This is from lesson 10, possible equation. So an exponential function can give us information about a graph that represents it. For example, suppose the function q represents a bacteria population t hours after it's first measured. Q of t equals 5,000 times 1.5 t. The number 5,000 is the bacteria population measured initially at time 0. The number 1.5 indicates that the bacteria population increases by a factor of 1.5, and we can see Q graphed over here. Now, a graph can help us see how the starting population and growth factor influence the population. Suppose functions P and R represent two other bacteria populations and are given by P of t equals 5,000 times 2 to the t, and R of t equals 5,000 times 1.2 to the t power. Here are the graphs of P, Q, and R. All three graphs start with the same initial number of bacteria, 5,000, but the graph of R grows more slowly than Q because if you look at its growth factor, it has a smaller growth factor, so it's not growing as quickly as Q did. And then P has a steeper graph. It's growing faster because it has a larger growth factor than Q. If you look at P, it's doubling instead of just 1.5 times. So P grows the fastest because of the T. Q is in the middle because of the 1.5. And R is the last one. It's the slowest growing one because it has the smallest growth factor. So let's take a look at the cooldown. Here are three graphs representing three exponential functions, f, g, and h. Let's make some observations here. Well, first of all, g and h both share the same starting value. G is steeper than f, but not as steep as h. Based on all that, if f is 10 times 2 to the x power, and h is 20 times 4 to the x power, you should be able to figure out which of these starting values is correct and which of your growth factors will give you something that grows faster than this but slower than that. If you have questions, let me know.